the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for linear algebra students who are going through solution sets of linear systems. If you are working through a linear algebra course and just at the beginning, then this video is for you. However, you should have already been exposed to matrix equations and row reduction methods for this material specifically. Diving into this example, this is just an example video here. The augmented matrix for the homogeneous system that you see right there can be row reduced to the following. Now, normally I write this out just like this if I'm teaching it in class because I don't have the time in a linear algebra course, nor does your professor likely, to sit here and row reduce everything in your field of vision. However, because we are in an online environment, the least I could do is place this linear system into an augmented matrix and then just quickly show the row reduction. All right, so there we go. Now you can see through the row reduction process that it is actually row equivalent to this augmented matrix right here. Determine if this system has a non-trivial solution. If so, write the solution set as a vector. Now we know this system has a solution because it's homogeneous and it always has the trivial solution, but this is asking, does it have a non-trivial solution? Now personally, if I'm asked for a non-trivial solution, or better yet, if I'm just asked for a solution and I know that my system has a solution, then I'm going to get it into reduced row echelon form. And the way I'm going to do this is do two more steps. To get down to this form right here. And then you can go ahead and use equations from this point forward. Let me make sure the variables are correct. Yes, x1, x2, x3. I just didn't want to use x, y, z here. So we know that x3 is a free variable because the third column here is a non-pivot column. And we could have actually used one of our previous theorems here to just say we have an infinite number of solutions because according to theorem 2, if you're working on the lay text, if you're not working on the lay text, you have a similar theorem. It's just an existence uniqueness theorem for linear systems. But if a consistent linear system, which is what we have because it was ax equals 0, it's homogeneous, it's consistent. If it has no free variables, then the solution is unique, but we do have free variables. So therefore there are infinitely many solutions. And that means that we know our system actually had a non-trivial solution from the get-go. Without me writing anything down, because we knew that there was a pivot in column 1 and a pivot in column 2, but no pivot in the third column of the coefficient matrix, then we know from theorem 2, or again, if you're not in the same text that I use, an existence uniqueness theorem, that we have a free variable, and therefore this system has an infinite number of solutions. And so the answer to the question without writing any ink is to say, yep, it does have a non-trivial solution. It's more than just x equals 0, basically, that we do have an infinite number of solutions. The reason why I went through all of the solution here is because I knew that we had to write the solution set as a vector. So in other words, they wanted me to solve this. But if you pretend for a moment that they didn't have that sentence in there, then you could have stopped right at the beginning and said, I have a free variable because there's a column in the coefficient matrix that's not a pivot column, and therefore we have a free variable, therefore the linear system has an infinite number of solutions. It was consistent to begin with because it was homogeneous, and all homogeneous systems have the trivial solution at the very least. But again, we were actually asked to write the solution set. So that's why I went through the rest of this process and I got down to this right here. Now, one thing you should know about the question at hand, they're asking us to write the solution set as a vector. And you may be wondering, how the heck do I do that? Well, remember, our solution is x, and x is equal to the vector x sub 1 x sub 2 and x sub 3. However, x sub 1 we've just found out is actually x sub 3. X sub 2 is a negative 2 x sub 3, and x sub 3 itself is free. That is, it is just x sub 3. It's whatever we want it to be. Notice all three entries within that vector contain a common factor x sub 3 that I can move out front. And this is the solution set to the original system. It's whatever multiple I want of the vector 1, negative 2, 1. There's a little note at the bottom of this page. The trivial solution is obtained by letting x sub 3 just be 0. Otherwise, the solution set is a line through the origin and the vector 1, negative 2, 1. And that's shown by this figure right here. Except when you look at this, the way this figure is drawn, it's actually the opposite of that. The vector you're seeing right there actually is negative 1, 2, negative 1. But that's okay. It actually still goes through that same vector. It just continues down. So this is a line like this in 3 space. Now I just want to give a heads up because you might skip one of my future videos and just move past because, well, this might be low level to you and that's perfectly fine. But I do want to make a note here. Most professors, myself included, will ask you to parameterize this solution. In other words, I don't want the solution in terms of x sub 3. X sub 3 was part of the original unknown. So we generally parameterize that and say, well, let x sub 3 equal, let's say t. If you did that, your solution would be the vector x is t times the vector 1, negative 2, 1. It's called a parametrized solution. And again, there'll be a video in the future on that. Anyhow, the purpose of this example was really so that you know that homogeneous linear systems don't just have the trivial solution as their solution. They can have an infinite number of solutions. They have at least one solution, which is always the trivial solution, but they can have infinitely more solutions than that. And this was a great example of that. All right, I hope this helps you out in your linear algebra course. Have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.